Laplace transform. This is an interesting topic within linear systems. I say so because for the most part, in my opinion, it is a fairly easy concept, fairly easy knowledge area, especially when you get a good handle on the transform pairs. Okay. So I got this question asked by, I had this question asked by multiple students in my study guide, in my mini exams, in my on-demand course content, and so on. You would see that I repeatedly include u of t, step function, as being multiplied with a function. Now, students ask me questions like this. Can you please explain why you did not include 1 over s, the Laplace transform of u of t in the final solution? And I've explained this, right? So there are two ways to use the tables that are provided in the reference handbook. And this is sort of a subtle detail in between the line type of things. If you look at the title of the table that is provided in the NCES FE reference handbook, what does it say, guys? In the definitions of that table, right, as an intro preamble to that table, they call it as a unilateral Laplace transform table. Unilateral Laplace transform table, that basically means that it goes from 0 to positive infinity, right? Agreed? If there's a unilateral, there should be a bilateral as well. The bilateral will basically cover all the way from minus infinity to infinity. So the only transform tables that you can, pairs that you can use on the exam are the ones that apply to unilateral. And I explained this in the lecture in the course as well, that by multiplying a function, so let's say I have two functions. Okay, let me draw some Mickey Mouse function. This is a Mickey Mouse function. Okay, and then I have a unit step function. What is the quality of the unit step function? It has a magnitude of 1 for t greater than 0. Starts at t equal to 0 basically. It turns on at t is equal to 0, maintains a unit. Unity magnitude. So if I were to multiply these two guys, okay, let me actually extend the Mickey Mouse function to negative infinity as well. So when I multiply the Mickey Mouse function, my drawing is super bad. Okay, but this is a Mickey Mouse. Okay. So when I multiply the Mickey Mouse function with the unit step function, guys, what happens? What will be the result? The result will be the Mickey Mouse function, but starting at t is equal to 0, correct? It will basically mute everything that was below t is equal to 0. So that's what you're left with. So my response to the student was that the unit step function u of t emphasizes that the function f of t will turn on at t is equal to 0 and continue until infinity. Alternatively, I could have just included the function and said that it only exists as a unilateral, so u of t would not be required. This allows us to use a unilateral Laplace transform that is provided. And I included this because I received questions from multiple students about this. Make sense? Okay. Now Laplace transform, what have I told you about Laplace transform? It is one of the 3 transforms that we have to deal with, okay, that we have to negotiate with on the exam. Whether they ask you questions about the Laplace transform, Z transform, or Fourier transforms, I don't know, right? But this is one of the 3. So while dealing with the Laplace transform, these subtle differences, subtle details are very important. Having an understanding of how it is applicable to the LTI system, all of that is good stuff. But the most important aspect is correct application of the transform pairs. Does it make sense? And we have plenty of problems in the course work and the study guide to actually deal with that. All right. So the next question that I had that I received from the student, this has to do with the study guide 3rd edition 7.3D. Hey Wasim, can you please help me understand 7.3D? I thought that the constant 3 should be carried with the transform? This is the question. This is the function that we have. F of t is equal to this multiplied by u of t minus 3. The student also sent me her work, but I think that it was not important to include it in here, right? It was just a picture. So how do I go about solving this? Well, first of all, when I multiply this guy out, u of t minus 3 in here and u of t minus 3 in here, do you guys agree that this is what I end up with? Let me explain you the y of t and x of t in a bit, but this is pretty simple, right? So this is simple multiplication. Okay. Now, if you pay attention to this exponential and this exponential, if I define y of t as e to the power of minus t, do you guys agree then y of t minus 3 will be equal to e to the power of t minus 3? And over here, if I define x of t equal to e to the power minus 3t, then x of t minus 3 will be equal to e to the power of minus 3t minus 3. This is a simple substitution. Correct, guys? Yes? Now, why did I end up doing this? Because I am going to use the time shifting property of the Laplace transform. When I have a function which is time shifted by 3 multiplied with the step function that is time shifted by 3, the result will be the Laplace transform of the original function. So notice how I was able to cleverly extract the original function from here. So the Laplace transform of the original function multiplied by what? E to the power of minus 3s. Why minus 3s? Because the time shifting is by 3. In this case, it will be the product of the Laplace transform of the original function x of t, which is this guy, right? Laplace transform of this is pretty simple, e to the power of 3 plus s. We're going to use the beta function, I believe that's what it is. No, that's in the z transform. But yeah, for the exponential Laplace transform, pretty simple. And that's where the e to the power of minus 3s is coming from. Okay. So we have to take a step back in order to move 2 steps forward with this type of problem. Identifying this as a time delay problem is the key to unlocking the solution. Does it make sense, guys? Okay. So when it comes to Laplace transform, again and again, I'm telling you that knowing the tables, applying those pairs is going to make your life so easy, but it requires a little bit of work. It requires a little bit of practice and some basic level of understanding. Don't short circuit it. And the inverse Laplace transform, what is the extra step that you have to do in inverse Laplace transform? What is the extra step that you have to do in inverse Z transform? You guys remember? Yes, divide by Z in the Z transform. There's one more thing. Whenever we are dealing with the inverse Laplace or inverse Z transform, partial fraction expansion. Yes. Partial fraction expansion. And in the on-demand, I've helped you guys understand partial fraction expansion through 6 different scenarios, if I'm not mistaken. Okay, so please make sure that you spend time with those as well. So if you're working through the on-demand content, the lectures in which I have explained you the basics of Laplace, how it applies to LTI, we can do it via integration, but it is very painful, right? So use the transform tables, apply them properly, do enough practice problems in the quizzes, mini exams, homework assignments, study guide. When it comes to the inverse Laplace transform, you will still have to use the transform pairs in reverse order But before you get to that, you got to make sure that you are expressing things as a sum. Okay. So partial fraction, each fraction has been blown up and then you're looking at it as a sum. Okay. So an extra step involved both for Laplace and Z inverse transforms. Okay. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, StudyForFE.com.